in the year 1545, in the bustling city of Milan. A mathematician named Girolamo Cardano sat hunched over his desk, staring at an equation that seemed impossible to solve. The problem required him to find a number that, when multiplied by itself, would give -1. He knew that any positive number times itself gives a positive result, and any negative number times itself also gives a positive result. So what number could possibly multiply by itself to create -1? Cardano didn't know it then, but he was standing at the threshold of one of the most revolutionary discoveries in the history of mathematics. A discovery so strange, so counterintuitive, that mathematicians would call these numbers imaginary. Yet today, these so-called imaginary numbers are absolutely essential to our modern world. They power our smartphones, enable our wireless communications, help engineers design skyscrapers and bridges, and allow us to generate and transmit electricity across continents. This is the fascinating story of how impossible numbers became indispensable, how mathematical imagination became engineering reality, and how something that doesn't exist on the number line we learn in school turns out to be one of the most practical tools ever discovered. Our story begins not with acceptance, but with centuries of rejection and ridicule. For thousands of years, mathematicians worked comfortably with positive numbers. You could have 5 apples, 10 coins, or 100 sheep. These were real, tangible quantities. Then came negative numbers, which took much longer to accept. How could you have -3 apples? It seemed absurd. But eventually, mathematicians realized that negative numbers were useful for representing debts, temperatures below zero, and directions. But the square root of -1? That was a bridge too far for most mathematical minds. The ancient Greeks, despite their mathematical brilliance, never conceived of such numbers. The great Islamic mathematicians of the medieval period, who preserved and expanded Greek knowledge, also avoided them. Even the innovative mathematicians of Renaissance Europe initially dismissed them as nonsensical. When Cardano encountered these impossible numbers in his work on cubic equations, he called them sophistic and as subtle as they are useless. He used them in his calculations, but only as temporary scaffolding that would disappear by the end of the problem. He certainly didn't believe they represented anything real. Another mathematician, Raphael Bombelli, made significant progress in the 1560s by developing rules for working with these strange numbers. He showed that even though they seemed impossible, you could add them, subtract them, and multiply them following consistent, logical rules. But even Bombelli saw them as mathematical curiosities rather than useful tools. The true turning point came with a French mathematician and philosopher named René Descartes. In 1637, Descartes wrote dismissively about these numbers and gave them a name that would stick for centuries: imaginary numbers. He meant it as an insult, a way of saying these numbers were mere figments of mathematical imagination, not truly real like the numbers we use to count and measure. The name stuck, but the insult backfired spectacularly, because imaginary numbers turned out to be far more real and useful than Descartes could have ever imagined. In the 18th century, a Swiss mathematician named Leonhard Euler made a crucial contribution. Euler was perhaps the most prolific mathematician in history, publishing more papers and books than anyone before or since. Among his countless contributions, he introduced a simple notation that would change everything. He decided to use the letter I to represent the square root of -1, yi. It stood for imaginary. But this simple symbol made these numbers much easier to work with. Instead of writing the square root of -1 over and over, mathematicians could now simply write I. And if you wanted the square root of -4, you could write 2i. The square root of -9 became 3i, and so on. Euler did much more than just create convenient notation. He discovered a profound and beautiful relationship connecting imaginary numbers to geometry, to exponential growth, and to the waves and oscillations that appear throughout nature. His famous formula, known as Euler's identity, has been called the most beautiful equation in mathematics, and it places imaginary numbers at the very heart of mathematical truth. But it was a Norwegian surveyor and cartographer named Caspar Wessel who, in 1797, made perhaps the most important conceptual breakthrough. Wessel realized that imaginary numbers weren't actually imaginary at all. They were just as real as ordinary numbers. They simply represented a different dimension. Think about the number line you learned in elementary school. 0 sits in the middle. Positive numbers march off to the right. 1, 2, 3, 4, and so on forever. Negative numbers march off to the left. -1, -2, -3, continuing infinitely in that direction. This is the real number line, and it represents one dimension of numerical possibility. Wessel proposed something radical. What if there was a second number line, perpendicular to the first, standing at a right angle to it? On this second line, you would have the imaginary numbers I, 2i, 3i, and so on in one direction, and -I, -2i, -3i in the other direction. Now you had a two-dimensional number plane instead of a one-dimensional number line. Every point on this plane could be described by two numbers, a real part and an imaginary part. These combinations became known as complex numbers. For example, the complex number 3 plus 4i means you go 3 units along the real number line, then 4 units up along the imaginary number line. It's like giving directions on a city grid, 3 blocks east, 4 blocks north. This geometric interpretation transformed everything. Imaginary numbers were no longer mysterious impossibilities. They were simply the second dimension of number space, just as real and valid as the first dimension we call real numbers. The only thing imaginary about them was the unfortunate name that Descartes had given them centuries earlier. A German mathematician named Carl Friedrich Gauss further developed this idea in the early 1800s. And today, we call this two-dimensional number system the complex plane, or sometimes the Gauss plane in his honor. Gauss showed that complex numbers obeyed all the same algebraic rules as real numbers, but they also had additional geometric properties that made them incredibly powerful for solving problems. But here's where our story takes a dramatic turn from abstract mathematics to practical engineering. Because in the 1800s, the world was being transformed by a new force, electricity. Scientists and inventors were discovering how to generate electricity, store it, transmit it across distances, and use it to power machines. But electricity behaved in strange and complex ways. It flowed through wires, yes, but it also created invisible fields of force around those wires. It could be steady like a river, or it could alternate back and forth like ocean waves. This alternating current, or AC electricity, was particularly puzzling. The voltage and current would rise and fall in smooth, wave-like patterns, oscillating back and forth dozens of times per second. How could engineers calculate the behavior of circuits carrying this alternating current? The mathematics was incredibly complicated. Enter a self-taught electrical engineer named Charles Proteus Steinmetz. Born in Germany in 1865, with physical disabilities that would have discouraged most people from pursuing ambitious careers. Steinmetz emigrated to the United States and went to work for General Electric. He became known as the Wizard of Schenectady, and his magic wand was the imaginary number I. Steinmetz realized that alternating current could be beautifully described using complex numbers. The real part of a complex number could represent the voltage or current at a given moment. The imaginary part could represent how that voltage or current was changing, its rate of oscillation and its phase. Using complex numbers, Steinmetz developed methods for analyzing AC circuits that were far simpler and more powerful than anything that had come before. Problems that would have required pages of complicated trigonometry could now be solved with a few lines of complex number arithmetic. He published his methods in the 1890s, and they revolutionized electrical engineering. Thanks to Steinmetz and his complex number methods, engineers could now design better motors, generators, transformers, and power transmission systems. They could predict how electricity would flow through complicated networks of wires, capacitors, and inductors. They could solve in minutes problems that previously would have taken days or been completely unsolvable. The entire modern electrical grid, which powers our cities, our homes, our factories, and our digital infrastructure, is designed using the mathematics of complex numbers. Every time you flip a light switch, you're benefiting from imaginary numbers. But electricity was just the beginning. In the early 20th century, physicists were making astonishing discoveries about the fundamental nature of reality. And at the heart of these discoveries were imaginary numbers. In 1926, an Austrian physicist named Erwin Schrödinger developed an equation that described how tiny particles like electrons behave at the quantum level. The Schrödinger equation, as it came to be known, was full of complex numbers, not as a convenience or a shortcut, but as an essential feature of reality itself. According to quantum mechanics, particles don't have definite positions or velocities until you measure them. Instead, they exist in what's called a superposition of possible states, described by a complex number called a wave function. The real and imaginary parts of this wave function combine in specific ways to tell you the probability of finding the particle in various locations or with various energies. This was shocking. The universe itself seemed to be written in the language of complex numbers. The imaginary numbers that Descartes had dismissed as meaningless turned out to be woven into the fabric of physical reality at its deepest level. Quantum mechanics, built on complex numbers, became the most successful scientific theory ever developed. It has been tested countless times and has never failed. It explains the behavior of atoms and molecules. It tells us why materials have the properties they do, why some conduct electricity and others don't, why some are magnetic and others aren't. It enabled the development of transistors, lasers, computer chips, and all of modern electronics. Your smartphone, your computer, your television. Every piece of digital technology you use exists because physicists and engineers understand quantum mechanics, which is fundamentally based on complex numbers. Now let's talk about signals and communications. Another area where imaginary numbers prove indispensable. When you speak, your voice creates pressure waves in the air. These waves are complicated, made up of many different frequencies combined together. A sound wave isn't a simple, pure tone, but a rich mixture of high pitches and low pitches. Loud components and soft components, all blended together. How do engineers analyze such complicated signals? How do they figure out which frequencies are present and how strong they are? The answer is a mathematical technique called the Fourier transform, named after the French mathematician Joseph Fourier, who developed the basic idea in the early 1800s. The Fourier transform takes a complex signal and breaks it down into its frequency components. It's like taking a musical chord and separating it back into the individual notes that make it up. But here's the key. The Fourier transform relies fundamentally on complex numbers. In the 1960s, mathematicians developed a lightning-fast version called the fast Fourier transform, or FFT. This algorithm made it practical to perform Fourier analysis on complicated signals in real time. And the FFT is absolutely saturated with complex number calculations. Today, the fast Fourier transform is used in virtually every form of digital communication and signal processing. When you make a cell phone call, your voice is converted to a digital signal, analyzed using the FFT to determine its frequency content, compressed to save bandwidth, transmitted through the air as radio waves, received by a cell tower, and then reconstructed back into sound at the other end. Every step of that process relies on complex numbers. When you stream music or video, when you use Wi-Fi or Bluetooth, when you take a digital photo or record a video, when you use GPS navigation or radar or sonar, you're using technology that depends on the fast Fourier transform and complex numbers. Engineers who design antennas use complex numbers to calculate how radio waves will propagate through space. The impedance of an antenna, its resistance to the flow of alternating current, is a complex number with a real part representing actual resistance and an imaginary part representing reactance. Electrical engineers use complex numbers to design filters that allow certain frequencies to pass while blocking others. Your radio can tune to a specific station because complex number mathematics allows engineers to design circuits that respond to one frequency while ignoring all the others. Let's move from communications to mechanical engineering and the study of vibrations. Buildings, bridges, airplanes, cars, and machines all vibrate. Sometimes these vibrations are harmless. Sometimes they can tear a structure apart. In 1940, the Tacoma Narrows Bridge in Washington State began oscillating wildly in moderate winds. The vibrations grew larger and larger until the entire bridge twisted itself to pieces and collapsed into the water below. The disaster was captured on film and became a famous cautionary tale for engineers. How do engineers now prevent such catastrophes? They use complex numbers to analyze vibrations and resonances. They model structures as systems with mass, stiffness, and damping. And they use complex number mathematics to predict how these structures will respond to forces like wind, earthquakes, or the rhythmic footsteps of people walking across a bridge. The imaginary part of a complex number in these calculations represents the phase of the vibration, how different parts of the structure are moving relative to each other. By understanding these complex relationships, engineers can design buildings and bridges that absorb vibrations safely rather than amplifying them to destruction. Modern skyscrapers, especially those in earthquake-prone regions or in locations with high winds, are designed using sophisticated complex number analyses. The Taipei 101 building in Taiwan, for example, has a massive pendulum near its top that acts as a tuned mass damper. This pendulum is designed using complex number mathematics to sway in exactly the opposite pattern to the building's motion, canceling out dangerous vibrations and aerospace engineering. Complex numbers are essential for understanding aerodynamics and fluid flow. When air flows over an aircraft wing, it creates a complicated pattern of pressures and velocities. Engineers use complex number mathematics to analyze these flows and design wings that generate lift efficiently while minimizing drag. The theory of complex functions, an advanced branch of mathematics dealing with imaginary numbers, provides powerful tools for solving problems about fluid flow. A technique called conformal mapping uses complex numbers to transform complicated shapes into simpler ones while preserving important geometric properties. This allows engineers to solve problems about airflow over oddly shaped objects by first transforming them into simpler shapes, solving the simpler problem, and then transforming the solution back. Every commercial aircraft, every military jet, every helicopter and drone flying today was designed using mathematics that depends fundamentally on complex numbers. Let's talk about control systems, another area where imaginary numbers are essential. A control system is any device or set of devices that manages the behavior of other equipment. The thermostat in your home is a simple control system. The autopilot in an aircraft is a complex one. The computers that stabilize a rocket during launch are even more sophisticated. Engineers who design control systems need to understand stability. Will the system settle down to the desired behavior, or will it oscillate out of control? Will it respond quickly to changes, or will it be sluggish? Will it overshoot the target and have to correct itself repeatedly, or will it smoothly approach the goal? These questions are answered using a mathematical technique called the Laplace transform, which is closely related to the Fourier transform we discussed earlier. The Laplace transform converts differential equations, which describe how systems change over time, into algebraic equations involving complex numbers. Engineers plot complex numbers on the complex plane to visualize the stability of control systems. If the complex numbers representing the system's behavior fall in certain regions of the complex plane, the system is stable. If they fall in other regions, the system will oscillate or become unstable. This complex number analysis is used in everything from the cruise control in your car to the flight control systems in modern aircraft, from industrial manufacturing robots to the systems that keep the International Space Station pointing in the right direction. Medical imaging provides another beautiful example of imaginary numbers in action. When you get an MRI scan, you're lying inside a powerful magnetic field. Radio waves are pulsed into your body, causing hydrogen atoms in your tissues to resonate and emit their own radio signals. These signals are detected, analyzed using complex number mathematics, including the Fourier transform, and then converted into detailed three-dimensional images of your internal organs. The entire process relies on complex numbers. The signals coming from your body are complex waves with both amplitude and phase information. The imaginary part of these complex signals contains crucial information about the tissue properties and the spatial location of the signals. Without complex number mathematics, MRI imaging would be impossible. In modern communications, a technique called quadrature amplitude modulation, or QAM, is used to pack enormous amounts of data into radio signals. This technique represents each piece of transmitted information as a complex number, with the real part controlling one property of the radio wave and the imaginary part controlling another. By using both the real and imaginary dimensions, engineers can transmit far more information than would be possible with real numbers alone. Your cable modem, your satellite TV receiver, your 4G and 5G cell phone, all use quadrature amplitude modulation based on complex numbers to achieve their impressive data rates. Let's consider wave phenomena more generally. Waves are everywhere in nature and technology. Ocean waves, sound waves, light waves, radio waves, seismic waves from earthquakes, waves in electrical circuits, quantum mechanical wave functions. Waves are a universal phenomena, and the natural language for describing waves is complex numbers. A wave has two key properties: amplitude, which is how big the wave is, and phase, which is where the wave is in its cycle at any given moment. A complex number captures both pieces of information perfectly. The magnitude of the complex number represents the amplitude, and the angle it makes in the complex plane represents the phase. When waves combine, when they reflect off surfaces, when they diffract around obstacles, when they interfere with each other constructively or destructively. All of these behaviors are most easily described and calculated using complex numbers. Engineers designing noise-canceling headphones use complex numbers to calculate exactly what anti-sound wave needs to be produced to cancel out unwanted noise. Scientists studying earthquakes use complex numbers to analyze how seismic waves travel through the Earth's layers. Physicists studying light use complex numbers to understand phenomena like rainbows, the blue color of the sky, and the operation of lasers. In modern digital signal processing, signals are often represented as sequences of complex numbers. Each complex number represents both the amplitude and the phase of the signal at a particular moment. Digital filters, which are used in everything from audio processing to image enhancement to radar systems, operate by performing complex number arithmetic on these sequences. There's a profound philosophical question hidden in all of this. Are imaginary numbers real? The name suggests they're not, but as we've seen, they're absolutely essential for describing and predicting real-world phenomena. Perhaps the question itself is flawed. Numbers in general are abstractions, concepts we invented to help us understand patterns in the world. The number 3 doesn't exist in nature. You can have 3 apples or 3 chairs, but the number 3 itself is an idea, a mental construct. In that sense, all numbers are imaginary in the philosophical meaning of that word. They're products of human imagination. But they're also real in the sense that they correspond to patterns and relationships that exist independently of us. The square root of -1, represented by I, is no more or less real than the number 3, or the number -5, or the number pi. They're all mathematical concepts that help us describe and predict the behavior of the physical world. And by that practical standard, imaginary numbers are supremely real. The story of imaginary numbers is, in many ways, the story of mathematics itself. It shows how abstract ideas, developed purely for intellectual curiosity, can turn out to have profound, practical applications. It demonstrates how initial rejection and ridicule can transform into acceptance and appreciation. And it illustrates how expanding our conceptual horizons, allowing ourselves to imagine new possibilities beyond our everyday experience, can lead to tremendous advances in understanding and capability. When Cardano first encountered equations that seemed to require the square root of -1, he had a choice. He could have dismissed them as meaningless and moved on. Instead, he worked with them, even though they made him uncomfortable, even though he didn't fully understand them, even though he doubted their validity. That willingness to work with uncomfortable ideas, to explore concepts that don't immediately make sense, to follow the mathematical logic wherever it leads, is the essence of mathematical progress. Today, imaginary numbers are taught to high school and college students around the world. They're a standard tool in the toolkit of every engineer, physicist, and applied mathematician. They're embedded in the technology all around us. Usually invisible but always essential. The next time you use your smartphone, listen to digital music, fly in an airplane, have an MRI scan, or simply turn on an electric light, remember that you're benefiting from imaginary numbers. These supposedly impossible, fictitious, imaginary quantities that mathematicians once ridiculed as useless have become the foundation of our technological civilization. The lesson is profound and worth remembering. Human imagination, human creativity, human willingness to explore ideas that initially seem strange or impossible, these are among our greatest strengths. Not everything that seems useless remains useless. Not everything that seems impossible remains impossible. And not everything that seems imaginary is actually imaginary. Mathematics has a remarkable way of revealing deep truths about reality, often truths that aren't immediately obvious or intuitive. The story of imaginary numbers, from their rejection as nonsensical to their current status as indispensable tools, reminds us to stay curious, to remain open to new ideas, and to recognize that today's wild speculation might become tomorrow's essential technology in the complex plane, where real and imaginary numbers unite to form a complete mathematical system. We find one of humanity's greatest intellectual achievements. We find a language capable of describing waves and oscillations, electricity and magnetism, quantum mechanics and signal processing, vibrations and flows, and countless other phenomena. We find that imaginary numbers, far from being figments of mathematical fancy, are deeply woven into the structure of our universe and absolutely essential to our understanding of it. So the next time someone dismisses an idea as imaginary, remember this story. Remember that the imaginary can become real, that the impossible can become practical, and that the greatest discoveries often begin with someone brave enough to ask, what if we imagined something that seems impossible? What if we took it seriously? What if we explored where it leads? The answer, as the history of imaginary numbers demonstrates, can change the world.